So my name is Dr. Eric Sortomme. My middle initial is V, and I did not have the foresight when I joined up as Rolo's Revenge in 2009 to the Tesla Motors Club to not be Dr. EVs. For some reason, I didn't even realize it till it was too late, but that's okay. More Rolos for everyone. So my talk is about the untold benefits of Tesla Energy. Tesla Energy, I can get into, we all know when Elon announced it, power packs for everyone, power packs for the world, and it was going to be this amazing thing how we're going to shift, we're going to store all our sunlight, and we're going to shift it to the peak demand, and we're going to meet all the energy stuff, and it can be for backup power, and everyone thought that's just completely amazing, and me, as a power system engineer, said, yeah, that's really cool, and there are so many other things batteries can actually do. And if you have a battery system now, just storing essentially sunlight and shifting it over is one of the least economical things that you can actually do with it, with a battery right now. So some of the things that you can do with these batteries is you can provide system ancillary services. You can provide power quality improvements to the grid. You can also do infrastructure deferments, and you can also use these batteries for integrating renewable energy systems. And yes, these beautiful things, they're 100 kilowatt hours and they're modular, and you can scale them up infinitely or you can distribute them all over. And it made me really, really excited, and for all the reasons that Elon didn't talk about. So here are some of these reasons. So the first one is ancillary services. You have this daily load, and you meet it by setting energy dispatch, those nice little red bars that you see. And that's how you schedule your power for an hour if you're in an energy market. But you see that doesn't really hit the entire load system. Even if you sort of moved the big peak over, you'd still have all that squiggly lines. And the reason is when you switch on a light switch, you don't call the utility and say, hey, I'm going to turn on 100-watt light bulb, please ramp up accordingly, 3, 2, 1, go. And so the utility is constantly adjusting their outputs of all their generators to meet this. And so we call this sort of our frequency regulation. And you've got a battery, and it can be set to respond quickly to do this stuff. And regulation is sold in deregulated places in the market. So Cal ISO has one, PJM has one, Midwest ISO, Texas has one. And so this is actually a very valuable service that fast-acting resources like batteries can do. So it can just smooth out your power grid and make a bunch of money. And so utilities would love batteries to do this. Say, what happens if you lose a chunk of power like you saw right there? You still need to meet it. There's this emergency reserves that you pay these generators to operate not at their optimum efficiency. Just in case one generator trips offline, you can bring them all up. But if you have a whole bunch of energy storage batteries, you can just say, oh, we'll just keep enough backup storage energy in all these batteries in case it's ever needed. We can ramp it back up. And so this is a valuable service that these batteries can do to set the other generators that are working right now. Yeah, it's going to take time to phase out the fossil generation, but once we start putting batteries out, we can get all the fossil generators working at their peak efficiency before they phase out. So it gets more bang for its buck right away and more money to the people that buys it. Power quality issues. Voltage. So if you're on a distribution line, we've got this nice little line circuit there. As you go further down, your voltage drops. And this can cause, as they try and regulate this, sometimes you can have some houses really close to your substation that have a voltage that's too high, and some of them that are too low. And it just gets a problem of trying to manage this voltage as the power flows down. You have a voltage drop, and you can inject power from a battery, and that can raise your voltage at a localized spot. So if you find a place where the voltage is too low, you can pop a battery there for your energy storage, and whenever you're injecting, it raises the voltage. And if you are charging a battery, it will make your voltage drop more, so you can sort of do this voltage regulation by injecting power or sucking it in. But you can also control it using something called reactive power. So this is, I'm going to talk about imaginary power. So here's a wonderful equation for power, and you see the P is the real power that you pay for, and the J is the imaginary number, and that's attached to reactive power, and you never see this on your bill because, as an engineering professor of mine said, do we pay real dollars for imaginary power? And no, we do not. But what does it mean? It's how hard your power has to work against the system to get from a generator or a battery to your house. It's kind of like a road. You see these 3 roads? If you have no reactive power, you're on the far left. You're the highway, and you're nice and smooth, and it's easy. If you want to drive a mile, you get optimum efficiency. And as you get more reactive power on your system, you go from like gravel road to bumpy dirt road. And if you drive a mile with your car on the dirt road, even though it's harder, you're not technically going any further, but your car doesn't do it any more efficiently. So reactive power on the line is bad, and you want to get rid of it if you can. And batteries with their inverters can actually do this, and they can do it really well. And before this, utilities will buy big expensive things like giant capacitor banks to try and solve this reactive power problem, or they will buy giant inverters connected to small energy storage called a StatCom, and these cost millions of dollars, and they'll put them out there to try and control this voltage. And hey, now Tesla's selling a battery that you buy to store energy, and it can do this reactive power problem too. So congratulations. Infrastructure deferment. So sometimes you'll have an area like a city or maybe even a neighborhood that's on a single line far away from everywhere else, and as the load growth comes, suddenly that line becomes overloaded. And then you're looking at reconductoring miles to even hundreds of miles just because for 5 minutes or an hour a day, some days, this line could be overloaded, and that could cause a safety problem. But if you put a battery on that side, you can store up and do sort of this local energy shifting, and suddenly your overload problem goes away. And yes, the value of that energy might be really small, but not having to reconductor a line or put in another big transformer can save you millions of dollars, and you can push that infrastructure deferment off for years, maybe even decades, depending on how fast the load grows. And then that's, start putting the interest on millions of dollars over decades, and it's a huge savings once again. And there's lots of different devices in various locations and different things in the grid that can suffer this problem. And the beauty of 100 kilowatt hour modular, so you can do infrastructure deferment on a small localized thing with 100 kilowatts in a distribution system in some neighborhood, and you can even put megawatt arrays out for small cities that are on the end of long transmission lines and do all of this. And so it's going to be great for all the grid infrastructure. And the final is renewable integration. We know that they can store power from when it's windy to when it isn't windy, or from when it's sunny to the nighttime. But there's another problem that renewables have. So we see this a lot in places where you get big puffy clouds going over solar sites. You'll have a day that's it's partly cloudy, but all the clouds are thick cumulus clouds, and they flow over, and you'll have your solar site go from 100% power to 0% or 20% in a few minutes, and then it will pop back up, and it will start doing this constantly all day, or you'll have a gusty wind that just keeps blowing your turbines, ramping up and down and up and down. And the big system can handle this. That variation isn't too bad, but locally, you'll start having all this flicker in your lights, and it can really put a stress on transformers or other industrial equipment or motors that are connected to the distribution line. But you can set your batteries to a smoothing mode and stick them right by the solar site, and the battery fast acts in the opposite direction of the solar and just smooths that out. So what you have to the rest of the system is a nice smooth output. It might gently go down and gently go up, but the equipment can handle that and your lights won't flicker. And so then the batteries can just solve this other renewable integration problem. And so in the conclusion, power packs don't just provide energy shifting and backup power, they do a whole host of other things. And so it doesn't just solve the renewable problems, it solves almost all of the problems that we have on the grid currently, with improved power quality, making energy cheaper, making everything last longer, making the grid more flexible. And so they've always said that cheap modular energy storage is the holy grail of the power grid. And basically, the Power Pack is that. So, thank you.
Thank you, Eric.